What we're going to do now is we're going to tie up all these different probability distributions and these sampling techniques and being able to convert stuff to standard normal distributions all together using something called the central limit theorem. So what we've pretty much seen at this point is we know if we have a standard normal distribution, we can use z-tables to figure out the probability of being less than a certain z-score, being above a certain z-score, or even being between two z-scores. So you utilize that table to figure out the area, which gives you those probabilities. If we don't have a standard normal distribution, but we do have a normal distribution, then we can in turn make it standard by using that z-score conversion. So that's where you take x, you subtract the mean, and divide by the standard deviation. Then we also saw all these different probability densities, and we saw that it's not necessary that you have a normal distribution. But what we were able to see that if we had a large number of data, we can do a sampling process and we can find sample means or we can find sample proportions. And by doing that and repeating that process over and over, we can get good estimators for those different statistics. And the real nice thing about creating those sample distributions is they tend to be normal. And so what the central limit theorem does is it actually gives us verification that's the case. So for all samples of the same size n, where your value of n is greater than 30, the sampling distribution of x can be approximated by a normal distribution. So that means when you create this sample, it's got to be a lot of data because you need your samples to be at least size 30. So if that's the case, then the sampling distribution of those samples x can be approximated with a normal distribution with mean mu, and we know it's the exact same mean because we know it's a good estimator. And then its standard deviation is really the previous standard deviation, but we're going to divide it by the square root of n, which is that sample size. So what I want to do is I'm going to show you some real life examples of how this ends up working. So this picture kind of just gives verification of that. There were originally data collected from 1,000 different Boston commute times. And then if you look in the back of your textbook, you can see the actual list of all of the data. When you go to plot that, it creates a histogram that looks like this, which is definitely not normal. But instead, what we can do is we can create a histogram of 1,000 sample means. And from these 1,000 data values, each sample included 50 different commute times. So from the original 1,000, they'd pick 50 at random, they'd find that sample mean, and then they'd plot it. Then they repeat the process, pick 50 more different data values, find the mean of that, plug it in that histogram. And you can see what results is something that is symmetric and does have that normal distribution, which is fantastic. Because again, I can find probabilities with a normal distribution by using those z-scores. That mean is right here in the middle, and so I could easily figure out what's the probability that I would wait less than 36 minutes in traffic, or the probability that I'd wait more than 36 minutes by finding that z-score and finding the area under the curve over here. But the key thing to take across here is that you need that sample size to be greater than 30, okay? So really this central limit theorem is going to apply in two cases. If the population is already normally distributed, then you can go ahead and you can immediately do exactly what we've been doing before. But your mean will still be mu, your standard deviation, because you're picking a sample, is going to be the square root of n in that denominator instead. Or if your sample size is bigger than 30, then you can use the central limit theorem. You need at least one of these to be true. If they're both not true, then you cannot do this process. You will not be guaranteed that you end up with a normal distribution in the end. So if either of these is not true, the distribution of those sample means cannot be approximated well by a normal distribution, okay? So we've already gone through how to create that probability distribution with sample means. That was our prior section. So what we're gonna do now is really just kind of talk about how we can apply the central limit theorem. So the very first thing is you need to be given your population. It can have any distribution, which again, it could be normal, but it's going to be given an actual true mean, mu, and then a true standard deviation, sigma. From this population, we're going to get simple random samples of the same size, n, from the population. And again, it's important, this value of n has to be greater than 30 if you didn't have something that was normal to start with. Okay. Then once you have all of those random samples, you're going to find the sampling distribution of the sample means x. So that means you're going to go through from each individual sample, you're going to go ahead and take the mean, and then you're going to find the probability at which that specific mean occurs. So your population, your main requirement is the population has to be a normal distribution, or that value of n needs to be greater than 30. As long as one of these is satisfied, you can apply the central limit theorem. But in some cases, you do need n to be larger. This is not something we're going to put a ton of focus on. If you were going a lot further in statistics, then you would. But in some cases, you may need n to be larger. Okay. So from here, we're going to go through a couple different definitions. So once you have that sample and you find those sample means, the mean of all of your values of that sample distribution is again just your regular mean, but we're going to denote it with mu sub x to indicate it came from the mean of the sample values. It still is going to equal that true mean, okay? Then once you have all of your actual sample means, then when you find the standard deviation of all of those values, we're going to call that sigma sub x bar. So it's the true standard deviation divided by the square root of n. So now when you have your mean and you have your standard deviation for the sample, we can find the z-score for that. So the z-score conversion for that value of x is going to be whatever your sample mean is minus the mean, which is mu sub x, divided by sigma sub x. So really the formula for this is x bar minus mu over sigma, the true standard deviation, divided by the square root of n, okay? So as just a little note, this often has another name associated to it. So we're gonna fit that right in here. Sigma sub x bar is called the standard error of the mean. And is denoted often by STEM. Okay. So again, in this situation, you're going to be given those distributions already. You don't have to go through and find it like we did before. When you have your mean of your sample, it is the true mean. To find your new standard deviation of the sample, you take the true standard deviation, and now you account for the fact that this is a sample, so you divide by the square root of n. And then your z-score is found in the same way. For that sample, you subtract the sample mean, divide by the sample standard deviation. And then really all of these prior methods that we use to answer questions with the z-score conversions can be used from here. So I know this process seems like it's a lot, but I promise in practice for what we're going to do, it's not too terrible. We're really just tying everything we've learned in together. So we're going to start with an example. Assume that females have pulse rates that are normally distributed with a mean mu of 77 beats per minute and a standard deviation of sigma being 12 beats per minute. We want to figure out if one adult female is randomly selected, we want to find the probability that her pulse rate is less than 83 beats per minute. Okay. So one of the things we have to figure out is it a sample or is it just a standard real population problem? And because I'm only working with one adult female being selected, we're going to use our regular distribution to figure out the probability. So since this is a single individual, and not a sample, we use our regular population distribution. To determine the probability. Basically meaning we use our normal z-scores. So in this case, our mean is 77 beats per minute. Our standard deviation is 12 beats per minute. And we're specifically looking for what's the probability her pulse rate is less than 83. So our value that we're searching for is 83. So if we have our normal distribution, try to make this as symmetric as I possibly can, not too terrible. 77 is the number right in the middle, and we're looking at her having a heart pulse rate of less than 83. So we are searching for what is the area here. So these are our X values. I want to go ahead and I want to convert them to z-scores instead. So I know 77 is going to convert to 0. And if I find my z-score corresponding to this, it's going to be X minus the mean over sigma. So it's 83 minus the mean of 77 divided by 12, which gives me 6 over 12. So this value is 0.5 away from the mean, 0.5 standard deviations away from the mean. So using the z-table, the area to the left of z equaling 0.5 is, well, I need to go to my z-table for that, and I have that at the very end. So I need to go to the positive values, and 0.5 is right here. So that's 0.6915. So the area to the left is 0.65 or 6915. Okay. So the probability, her heart rate or heart pulse is less than 83 is exactly this value, 0.6915. Again, exactly what we did before, because this was a single individual and not a sample, we just immediately found the z-score. But now in this next one, if I change this and say if 9 adult females are randomly selected, we want to find the probability they have pulse rates with a mean less than 83 beats per minute. So again, here I'm now searching a mean pulse rate, and I have 9 females. So what this means is this is a sample of our data. So in that case, we have to use the central limit theorem. To find our z-score. So one thing I do have to verify, if I'm using that central limit theorem, it's got to be valid. So my sample is 9. That's definitely less than 30 that I needed. However, back up here, they do tell us that females have pulse rates that are normally distributed. So I do have normally distributed data. The central limit theorem is going to apply. So here, even though n, our sample size, is 9, which is smaller than 30, this data is normally distributed. So the central limit theorem applies. If you are using named theorems, you have to verify that you actually can. Okay? So what I need to do here is find that z-score conversion. So my mean of the sample is the mean, the actual mean, which is 77 beats per minute. When I go to find the standard deviation of the sample, I take the true standard deviation and I divide it by the square root of the sample size. My true standard deviation is 12 and my sample size is 9, so we divide this by the square root of 9. Thankfully, that is a nice number. Square root of 9 is 3. So if we take 12 and divide it by 3, it gives me 4. Okay. So ultimately, I have a new z-score that I'm going to find based on this data. I'm still looking at the same information. If here are my sample data, it's got a normal distribution. 77 is still in the middle, and 83 is still the number I'm looking at. And I want what's the area under here. The main difference is I have a different standard deviation. So when I go to find my z-scores underneath this, when I convert over my 83, my z-score is 83 minus 77 divided by 4 instead. Right? Because the reason for that, you still find it the same. It's your value minus the mean divided by the standard deviation. It's just the ones that are associated with the sample instead. So if we go through and do this, 83 minus 77 is 6. 6 divided by 4 gives us 1.5. So this z-score is 1.5 instead. So you can see that changes slightly, even though I was looking at the same thing. This was only 0.5 away from my mean. But now when I'm dealing with the sample, this mean is 1.5 standard deviations from the mean. So now I can use my z-table. The area to the left of 1.5, and hence the area to the left of 83 is as follows. So again, I have a positive z-score. I need to go to my positive chart. Going to 1.5, I don't have anything after that, so that would be 0.9332. So this is 0.9932. I'm sorry, 9332. Can't speak and remember easily. Okay. So that tells me the probability that the sample mean of 9 individuals being less than 83 is 0.9332. So the probability, the mean of 9 randomly selected females having a pulse rate less than 83 beats per minute is exactly the 0.9332. So there is a 93.3% chance when you draw 9 females randomly that their collective mean heart or mean pulse rate is less than 83. Okay. So you can see, again, it's not much different than what we did before. The only new thing is you have a different standard deviation to find when you have a sample. So we're going to try one more example. Again, has 2 parts. And this is basically a nice way to kind of show you that safety of things is important and how they use statistics to be able to determine whether something is an appropriate kind of load for a device. So if you've ever gone for room capacities, there's always like fire hazards. It has a capacity of this. Elevator, same thing. It gives you a max number of persons, but also a load capacity, because it's basically using statistics to figure out what the average individual is. So this problem states, a boat capsized and sank in a lake. Based on an assumption of a mean weight of 141 pounds, the boat was rated to carry 75 passengers. After the boat sank, the assumed mean weight for similar boats was changed from 141 to 173 pounds. So kind of to summarize what that means is 75 people could come on this boat because they assumed that each of those persons, if you were to find their average weight, it was 141 pounds. And so you would have no problems with the boat staying afloat, you were good. But realistically, if you look at human data, most individuals are above, or most adults are above 141 pounds. So ultimately it was changed to 173 pounds as an average weight for 75 passengers. So what we want to do is we kind of want to just take a deeper dive. And if I assume that this sample of 75 individuals has certain properties, so we're going to assume that human weights are normally distributed with a mean of 175.8 pounds and a standard deviation of 37.1 pounds. We're going to find the probability that the boat is overloaded because the sample of 75 passengers has a mean weight greater than 141 pounds. And then we're going to see, well, if I assume they have a mean weight of 173 pounds, what's the chance of it being overloaded? So essentially here, we have our true mean for our population and true standard deviation. And we're dealing with a sample of 75 random people going on this boat. So we're going to see what is the probability that they have a mean weight more than 141 pounds, because that's the chance of the boat being overloaded. So here our sample size is 75, which is definitely greater than 30. So I can use the central limit theorem, but also I can use the central limit theorem because the weights are normally distributed. So my n is greater than 30 and the data is normally distributed. So the central limit theorem applies. So my population size is 75. My mean of this sample is the true mean, which is 175.8 pounds. My standard deviation of the sample is the true standard deviation divided by the square root of my population size. True standard deviation is 37.1 pounds. And when we divide that by the square root of 35, you plug this into your calculator, that's about 4.283939. Okay. So drawing a little picture as to what's going on here and what we're actually trying to do. Here is our normal distribution for the sample. It's got a mean in the middle of 175.8 pounds. And I want to see what's the chance of this mean sample being greater than 141. 141's to the left, so it's definitely going to be a negative z-score. But I want to figure out what's the chance the average weight of these individuals falls into this area. So I need to convert this to my z-scale instead. In the center is 0, but my actual z-score is going to be my 141, which is my sample size or my sample thing I'm looking for, minus the mean of my sample divided by my sample's standard deviation. So I'm going to take that 141, which is what I want that mean to be, subtract 175.8, and then divide it by my sample standard deviation, which is 4.283939. Again, I didn't round there because I wanted to go as many decimals as I could. But now when I actually get my z-score, I only have to go to 2 decimal places. So this is negative 8.12. So it is 8 standard deviations to the left of the mean. And now if I go to my z-table, realistically, the smallest z value I have is negative 3.0 because everything after that is 0.0000. So it is so microscopic, that area underneath. So the area to the left of negative 8.12 is 0.0000 when you round it. Okay. So our chance that the average weight of 75 passengers being more than 141 pounds is 1 minus this area, which is 1. So the probability, the mean weight of 75 passengers being greater than 141 pounds is 1 minus 0, which gives you a probability of 1. So pretty much it is guaranteed that boat would sink because they used the wrong mean weight. Okay. So as a result, you obviously can't have as many individuals. 75 is too much. So instead, the boat was later rated to carry 12 passengers, having a mean weight of 173 pounds. So we want to see with this new information, if the 12 individuals chosen at random, having a mean weight of 173 pounds, we want to see what's the probability of it being overloaded because that weight is more than what they assumed of 173 pounds. So again, I can still apply the central limit theorem because I'm working with normal distributions here. In this case, my value of n is 12, which is definitely smaller than 30, but the data is normally distributed. So the central limit theorem applies. So my sample size is 12. My mean of the sample is my true mean. It's still the 175.8 pounds. My standard deviation of the sample is going to change because it is the true standard deviation over the square root of the sample size. My true standard deviation is 37.1. My sample size here is 12. So again, I'm gonna go out a lot of digits because I'm not at a point where I'm getting an end result yet. So if I plug this into my calculator, it's about 10.709847. Okay. So drawing my little picture for what's going on, here's my sample data with my normal distribution. The 175.8 is still the mean in the middle. And they assumed that the average weight of the individuals on the boat is 173 pounds. So I am looking for this area here, and this is the probability that my boat would capsize or sink. So I need to find the associated z-score. And again, it should be negative. So my value of z is going to be my mean that I'm given minus the mean of all of my samples over my sample standard deviation. So the mean we assumed is 173 pounds. Subtract 175.8, which is the mean. And we figured out the sample standard deviation is 10.709847. So if you plug this into your calculator, your z-score is about negative 0.26. So the area to the left, using that z table, is the following. I need to go through and I need to look at negative 0.2, which is all the way down here, and that's 0, 1, 2, 3, 4, 5, 6. So this is negative 0.26. So 0.3974. So our probability of the boat overloading is 1 minus that, because the 0.3974 is right here. So the probability of the boat overloading is 1 minus 0.3974, which is 0.6026. So even with this, there's still about a 60% chance that the boat can capsize, when they cut the passengers down to 12 and assumed a bigger weight, because they still used a weight that was less than the true mean of individuals. So really still not a great safety measure. They probably need to cut the load down even more than that to guarantee there's like a 98% chance the boat won't capsize. Because you want to be very careful and conscientious when you have potentially lives at risk. Okay? So hopefully this kind of ties everything we've done in together. But it's a really nice way to see how we can turn other distributions into normal and utilize these Z tables to gain insight into what's going on.